Hello and welcome back to Lab 1 on basic skills in Matlab. We're going to start here today by talking about low-level file I/O in Matlab. And I would say that if you're familiar with the C programming language, the way that low-level file I/O is handled in Matlab is the same way it's, or that Matlab is modeled after the file I/O that you find in C. So in the code that's shown here on this slide, I have a file creation and a file read example. So it looks like we're going to take the read first. So to read a file, a binary file, you use the fopen command to get a handle to, this is the equivalent of a file pointer. It gets you a handle to the file inside of Matlab. So you use single quotes to describe the file name, and then you pass RB indicating that we're going to read a binary file. If the fopen command fails, it returns a -1, so you can check that and report an error if the file is not open. Of course, you can't do a read on a file that's not open, so it's a good idea to check that and report a message, an error message. Once the file is open, you can use the fread command to read in values. So, and of course, you have to. So this command, for example, here on line 3, reads from this file 5 integers. Integers are 4-byte objects, and so this reads 5 of those kinds of objects into this member variable, or this workspace variable called x. And it returns, if for some reason it wasn't able to read 5 of those, it returns a count that you can check and see how many it actually read in. Maybe it encountered the end of the file before it was able to read in 5, and so it would only count would be equal to 4, for example, possibly. The next line, on line 4 here, we read from the same file 10 floating point values, and just to illustrate the kinds of things that you can do here, on line 5, this command fread from this file, values that are type short, so this is a 16-bit signed integer, and then if you put inf here in the second argument, it will read until the end of the file and treats everything that it encounters like a 2-byte short integer. And then when you're all done, you can close the file. If you, of course, as in all things, if you're interested in getting more information, more details on fread, you can just type help fread at the Matlab command line, and it'll give you a long, several pages worth of information about how to use this function. Down below here, I'm going to create a file and put, it looks like, random, uniformly generated random numbers, 10 of them, into that file. So I, again, open a file. In this case, I will use the WB, so that indicates that we're going to write a binary file. So this will create a file, or it will overwrite the file if it exists. And you can do other things, like you can append to a file, and you can write text instead of binary, and so on and so on. But in this case, I'm opening it to write binary data, and I'm writing to that file. I should check to see if it's open before I write to it. But I'm going to write this array y, so that's going to write 10 values. It's going to format them as type floating point. Even though inside Matlab they're actually stored as double precision numbers, when it writes them out, it's going to convert them to floating point numbers, single precision floating point numbers. And fwrite returns the number of values written, and then you close the file. All right. The reason that we're interested in this kind of low-level file I/O is that we're going to use the multimedia accessing capabilities of Matlab to read media files in, and then we're going to take the data and we're going to write it out using this low-level file I/O type operations that you see here to raw binary files. Then we'll read the binary files into our C programs, do the processing, write them back out to raw binary files. Then we'll read those binary files back into Matlab and look at the results, either make plots, or if it's sound, maybe we'll listen to it, or we can always take those take those signals and write them out to image files or audio files, video files, whatever the case may be. So once again, we're going to use this sort of capability quite a bit in MATLAB, and you should become familiar with reading and writing. This should be second nature. And if you're familiar with the C programming language, then you've probably seen this sort of stuff before. Like C, there are other file I/O type functions available. You can do, there's a whole bunch listed. You can seek, you can rewind a file that's open, you can check for errors, and so on. So this is the only slide I have on low-level file I/O. Again, if you have questions, consult the help system, and there's much more information there. Okay, so to this point in Lab 1, we've talked a lot about signals, we've talked about multidimensional arrays and accessing them, creating them. We've looked at examples of reading signals in from media files and how they populate multidimensional arrays. We've talked about low-level file I/O, and now it's time to turn attention to some of the visualization capabilities built into MATLAB. We're going to look really at two basic capabilities. The first one is making plots of signal waveforms, so one-dimensional plots like audio signals, and then we'll also look at making two-dimensional plots, which are images or video frames, and then we'll look at creating some special plots. For example, spectral plots. These will be plots of the Fourier transform of signals, which are going to be calculated in the computer. And we'll also look at what are called spectrograms, which are images that show how energy is distributed across both time and frequency. So these will be useful tools to us as we try to understand and look at signals. I mean, it's a good idea to look at signals in the time domain, but we also need to be able to visualize what's going on in the frequency domain as well. So first, the plot command. And again, if you've used MATLAB, it's very likely that you have already used the plot command and you're familiar with it. But essentially, plot creates a set of points in an axis and connects those points with straight line segments. And then you can decorate these, you can change the colors, and there's all sorts of other things that you can do. You can add multiple plots to the same axis, so you can have multiple lines in the same axis. And that's described here. Essentially, with plot, you provide the coordinates of the points in a pair of vectors. One is for the x-axis, one is for the y-axis. And it's pretty straightforward. If maybe an example would help. So I'm going to use the colon operator to create a vector x from minus pi. We'll have 101 points up to pi. I'll create y1 to be cosine of x, y2 to be sine of x, and y3, for example, to be hyperbolic tangent of x. Then we can say plot x comma y1, x comma y2, x comma y3. That will put all three of those plots on the same axis. As you see here. Let's see what else. You can do a similar sort of thing by saying plot. I mean, sometimes you have a plot that you like. Here we have a plot of a cosine wave, and we want to add another plot on top of this, so we could say, hold on, plot x comma y2, and we might want to plot that one in red, so I'll use the color identifier there. And then finally, while I'm at it, I'll go ahead and add y3. Maybe I'll put that in green, and then I'll hold off. So you can toggle the hold state of an axis by using hold on and hold off, and then subsequent plot commands are added to the same axis. Okay, I think that's enough. If you look at the help on plot, there are some built-in colors that you can use, blue, green, red, and so on. You can also identify the markers that are used. So suppose we wanted a pentagram at each of the points. Let's go back and we'll say plot x comma y1, and we'll say RP. So this will draw red pentagrams at the points instead of connecting them with lines. Looks like little stars. If you would also want to have let's go ahead and do the same thing, but now we want the line to be blue underneath, so we'll have a blue line with red stars on top, and you can see that that's in fact what we get here. So again, plot creates points and connects those points with straight line segments, and then from there you can just embellish and decorate as you desire. The next thing to be aware of is it's useful to have some basic capability with MATLAB's handle graphics. So each plot, for instance, each line plot that is added to an axis, let's go back and we will get a handle. So the plot command returns a handle to the object, and again it just makes a plot. But if you want to see what attributes of that plot you can modify, you type get hand. So this returns all of the attributes of that plot. So if you just look at a few of these, we don't have to pay attention to all of these, but it shows the color. This is drawn in red. So this color triple is R, G, and B. So for example, if we wanted to change the color, I could say set hand color 0.50. So this sets it to sort of a mid-range green color. So you can see that changed the colors. What else is there that we can do? We can change the line width, we can change the marker, we can change the marker size. We could say set hand marker and we could say 20. This will make much larger stars at each of the points. We could make it anyway, there's a variety of other things that can be done here. Oh yes, the other thing is sometimes the other thing that's useful is if you don't know what values are legal here, you can type set hand with no arguments, and it will actually not just show you what attributes there are, but it will also show you what options there are for those attributes. So for example, we could turn on the line style. Currently there is no line, but we could set the line style to dash, or maybe we should set it to colon. Set hand line style colon, and it's very hard to see, but it added a dashed line in between the stars. So again, set hand with no arguments will not only show you what attributes can be modified, but it will also tell you what the options are for each of the attributes. Okay, so those are some things that are useful to know. Let's go back to the Matlab figure window for just a minute. So this window is a figure. The figure contains an axis, that's the axis that you see here, and the axis contains a plot line. And so there is a natural hierarchy. Figure contains axis, axis contains one or more plot lines. In fact, a figure could contain multiple axes, and you can add multiple axes in a variety of ways. The easiest is probably using the subplot command. Some of the useful commands for figures are GCF. If you type GCF, it clears. Oh no, that does a get current figure. If we type CLF, it clears the figure window so that now it's blank. It removes the axis and the plot. Let's put the plot back in there. Let's see, what else do we want to look at here? Yeah, if you want to modify the properties of the figure window, you can type get current figure, and this will show you what the different things that can be modified. If we type set get current figure, it will show us the different things that can be the attributes of the figure that can be modified. So you can move it around on the screen. You can change the internal margins, the position. The position is controls the positioning and the size on the screen. Let's see, one of the things is color. So we could notice how the figure window has this gray color in the background. We could change the color set get current figure. That returns a handle to the current figure. Then we could say color, and we could then give it a triple 0.5, 0.5, 0.1. So that makes the background color for the figure whatever that color is. So anyway, yeah, you can change many of the properties of the figure. You can, just like you can change the figures of the attributes of the plot. Some useful commands. Sometimes you get lots of figure windows open, and you would like to close the figure windows. You can do something like close all. That gets rid of the figure windows. It's no longer in existence. Let me put the plot back up. You could, let's see, what were the other things that I wanted to call your attention to? You can clear the figure window, that's CLF. GCF, that's get current figure. If you just type figure, that creates an empty figure. This one here I've learned about recently, which is useful if you are in Matlab. So sometimes you get lots of figure windows open. You might have 20 windows open, 20 figures open. And you just made a plot, and you want to raise to the top the figure window where you just did your plot. So if you just type SHG, that raises to the top the figure where the most current plotting commands were plotted. So those are all useful things relating to figures. So underneath figures there are axes. GCA returns the handle to the current axis, and the axis has very many attributes that can be set by the user. If we type set GCA, it will show us the attributes that we can set, and it will also show us some of the options that are available. And there's just a ton of them here. Color, you can set the font size, the font name, the font angle. You can set the font weight, bold or normal. You can set the transparency, which is the grid alpha. You can create user interactions when users press the buttons in that figure or in that axis. You can create let's see, where is it? You can create labels. You can define where the tick marks are, whether they poke in or whether they poke out. All sorts of things are available for an axis. I won't bother going into all of the details at the moment. But anyway, handle graphics are extremely useful, and it's a good idea to become familiar with some of the handle graphics things. Another way, let me just point this out too, another way that you can edit figures without having to do a lot of typing is if you click on this little button here, it opens, and again, maybe many of you are already familiar with this, but it shows in a graphical interface the plot and the figure, and you can go in. So for example, if you select the axis, you can say show more properties, and then you can just see all of the properties listed here. And some people like to go in and modify these by hand using the graphical interface. In a programmatic sense, it's easier just to use the handle graphics. And so, for example, if I wanted to change the color of the axis, I could just choose a color. And why did it not work? Oh. So yeah, it colors in the axis whatever color you choose. So this can all be done graphically as well. Some of the functions that I use frequently are listed here. So some of the things that I like to do often are grid on. Oops. That turns a grid on in the figure window. Actually, let me go back and change that because it's hard to see that now. So by typing grid on and grid off, you can turn on this grid. The other thing that, or other things that are useful is xlim. I can say 0 to 1. That sets the x limits to be 0 to 1. You can do the same thing with ylim. Let's see what else is listed here. Anyway, there's a large number of things. You can add labels to the x and y axes, and so on. So experiment, learn, and become an expert at visualization using plotting. As I said previously, you can add more than one axis to a figure window using the subplot command. So I could say subplot 3, 1, 1, plot x, y1. So what subplot does is it creates a grid of axes in the figure window with 3 rows, 1 column, and then this accesses the first axis, then the second axis, and the third axis in that grid. And you can see what I've done here is plotted a different function in each of those axes. So let's go ahead and take a look at that. And I guess I don't need this. Well, there we go. So we see the cosine, the sine, and the hyperbolic tangent. So to save paper, when you're making reports, sometimes it's nice to put a large number of axes on one figure. Okay. Finally, now that you have made a nice figure, figure that you want to save and include in a report, you can use the print command to print this to an image file format. You can save it as PDF. There's a large number of formats that you can specify. PostScript, encapsulated PostScript, you can make a JPEG image, TIFF image, PNG, PDF, and so on. Another thing you can do is use the orient command. So you can orient the figure landscape so it fills the page a little bit better. You can do rotated. Portrait is the default. Tall is like landscape, but it fills the page in the portrait mode. So those are some things you can experiment with as well. All right. Okay, so I think I included an example here. I don't want to belabor this. These slides are all available on the website. I've gone ahead and done some examples real time here within Matlab. This, if we just look at high level, what this is doing, it reads a whistle from a wave file into a variable called x. It creates a time vector so that we can plot x and see a true time-scaled axis. It looks like I do some subplots. I plot the signal, and then I also plot the signal again, and then use the xlim command to zoom in to just a small portion of the signal. I label the axes, I orient landscape, and then I print it to a PDF file. And this is what it looks like. So here you see the whistle, at least the first 3 seconds of it. And here I've zoomed in so we can see in a little bit more detail what the waveform actually looks like. I think I can actually demonstrate this one. This is a little oscilloscope program that reads in a wave file and then uses handle graphics to show different portions of the of the WAV file as if you were watching it scroll across the screen in real time. So notice what I do. I plot a portion of the signal, a small portion, and I save a handle to the plot. Draw now forces, so one of the things that you should be aware of is Matlab, when it receives plotting commands, does not refresh the screen until a time that is convenient for Matlab. So if you want to flush the queue and plot all of the, and force Matlab to do the plotting now, you use the draw now command. So this will, so often Matlab will wait till a program is done running before it makes any plots. But using draw now will force it to do the plots as soon as it encounters draw now. The thing I want to call your attention to, though, is here inside of the for loop. So notice I plotted just the first, let's see, WinSamp is the first 50 milliseconds of the signal. And then I go through this loop, and inside the loop, notice I don't do any plotting commands. But what I do is I set, I modify the plot line by setting its X data and Y data to different portions of the signal and the time vector, so that we'll see, and then I do a draw now, so that we'll see this thing look, it looks kind of like an oscilloscope when you run it. Oops, let me change that. First I'm going to clear the axis. I'll clear the figure, and then I'll run oscope again. And so we can see here everything's scrolling pretty quickly, so we can't get a good look at it. But if we go back into the code, let's see. And put this pause in, then we can run this and use the space bar to control how fast things scroll across the screen. So here, this gives us a close-up look at the waveform. This is, again, is a whistle, and you can get a very clear picture of what's going on with the waveform by zooming in and looking at this as a function of time. All right. Enough there. And again, so that's only possible in Matlab using handle graphics. Okay, moving on. Let's look at plots of two-dimensional signals, images. There are two basic commands to take a look at images. One is the image command, and the argument to the image command is a two-dimensional array, a matrix. It could be actually a three-dimensional array. We'll get to that here in just a minute. But if it's a two-dimensional array, it just plots, it's a grayscale image, and it just makes a plot of that image. You can add a color bar. You can set the color map. If it's grayscale, you can set the color map to be gray or jet or any of the other built-in color maps, or a custom color map that you make. If it's a 3D array that is passed in, it expects to see the third dimension have size 3, so that would represent the red, green, and blue color channels in a color image. Something to be aware of is this image. I don't often use the image command. I use another one that's closely related, because image is a little bit picky about the values that are passed in. If the entries in the array are double precision floating point, then they need to be scaled to be between 0 and 1. If they're unsigned integers, unsigned 8-bit integers, then they need to be in the range 0 to 255. So I think it's inconvenient to do that scaling. And so I often will use instead the image sc command. Let me show you what the image sc command has the exact same calling syntax as image. It's just that image sc scales the data to fit those ranges that were described previously. So here's an example of a grayscale image. On the left, I've made a plot down below of what that image actually looks like. Here it is in grayscale. This is what you would see if you viewed this in an image viewer. When you load that into Matlab, at least on my computer, the default color map is this color map called Jet. You can see it. It goes from a dark blue for a value of 0 all the way up to, at 256, kind of a dark red, and it runs through a variety of colors across the spectrum here. So instead of plotting, so this doesn't look like a grayscale image until you say color map gray. So here I guess I explicitly set the color map to be Jet. And this command on line 5 here, color bar, turns on this bar on the right side, so you can see, if you look at this, for example, spot in the image, and it looks like it's a very bright red, you can look at the color map and you can say, oh, the intensity there is about 250. Or these dark blue regions, you can look at the color map and say, oh, okay, those are about 0. One of the nice things that image SC, or the SC stands for scale, so image scale is this command. One of the nice things that it allows you to do is to clip the color map or clip your values, your input values, at some minimum and maximum values, so C low and C high. So you can see here the values coming in are between 0 and 255. Here again is the original image on the left. On the right, everything that was below 100 was set to 0, or black, and everything that was above 200 was set to white, was set to 200. So the color map now runs between 100 and 200, and again that's accomplished by, so you get kind of a saturated image. Sometimes that's what you want, and you can have that that capability is available here inside the image SC command. So once again, image and image SC are used to make pictures of two-dimensional signals. Let's see, I'm not sure if I have this one in Matlab. Let's take a quick look. I wonder what this one does. Oh, yeah. Okay, let's not look at that one yet. Here's how we use handle graphics with images. Once again, in this case, what I'm doing is I'm using Matlab as a movie player, and with these few lines of code and the use of handle graphics, we're able to view a video inside Matlab by just displaying each frame in an image, as an image. So we read in, well actually what happens here is I open a video reader object and I loop over each frame. So this read object 1 just reads in the next frame. The first time through, when I have the very first frame, I call image SC and get the handle. On subsequent reads, I use the handle to simply change the data being displayed in the axis. So you don't have to do this. You could call image SC every time, but that forces Matlab to do a lot of extra work, and instead of the video being displayed in a nice smooth way, it becomes choppy because every time it's creating a brand new image, a brand new plot. So again, when you use handle graphics, it doesn't create a new axis, it doesn't create a new plot. All it does is change the properties of the existing plot, and so you get this very smooth looking movie being displayed in the figure window. Alright, so we've talked about making plots of one-dimensional signals, using plot, two-dimensional signals, using image, and now it's time, and even videos. You can display a video and look at it a frame at a time in Matlab, again using the image command and handle graphics. So now we can visualize all these different kinds of signals, but all of the visualization we've talked about so far are time domain visualizations, or spatial. In the case of images, they're spatial domain visualizations. So it would also be nice, I mean, this is a course on signal processing, and we talk a lot about Fourier transforms. It would be nice if we could also look at these signals in the frequency domain. And computers can calculate Fourier transforms of signals, discrete time signals, and the function to do that in Matlab is called FFT. This stands for Fast Fourier Transform, and it's a computational algorithm that's very efficient. It actually does not use the formula that we write down when we think of the discrete Fourier transform, but it breaks the problem apart for efficient computation. And this is actually discussed in one of the chapters in our textbook, but we won't cover that chapter this semester. This, however, is covered in another course, Digital Signal Processing, Digital Signal and Image Processing, ECE 5630. So if you're interested in how FFT algorithms work, you can study that on your own or take a class. And you'll get to not only learn about it, but I think Dr. Budge also has you code your own FFT algorithm in that class. It's lots of fun. So let's take a look at this code, and then we'll see what it produces. At the top, we read in a wave file using the wave read command. Audio read can also be used. I choose an FFT size, which is a power of 2. In this case, it looks like I'm using 4096. I construct a frequency vector, and this is a true. So this frequency vector can be used to make a plot, and then we can read off of the x-axis the frequency in hertz. So this is a you can. And in fact, one of the reasons I wanted to walk through this is so that everyone would be able to know how to make a correctly scaled spectral plot in Matlab. So you choose an FFT size, you construct a frequency vector. This will depend on the sample rate of the data. Notice that the sample rate comes in from the wave file. And then you just make a plot. In this case, I'm doing 20 log base 10 of the absolute value of the FFT. And what that does is, what that means is we'll have a magnitude plot in decibels instead of linear scaling in volts or something. Then I adorn the plot with some labeled axes and make a plot. Let's take a look on the next page. So remember this signal, we looked at this earlier in the time domain, or a portion of this anyway, is a whistle. And a whistle is pretty close to a pure tone. And the Fourier transform of a pure tone, say a cosine, is a pair of impulses, one at the positive frequency and one at the negative frequency. You can see this is not a pure tone because we do have some energy leaking out into the nearby frequencies, but it's not too bad. It looks like from the x-axis we can determine that the frequency I was whistling at is about 2500 hertz. So anyway, when you create spectral plots, it's very useful to have a correctly scaled frequency axis with DC in the center, negative frequencies on the left, positive frequencies on the right, and you can have a magnitude in decibels, or you could have linear scaling if you leave off the 20 log base 10. But this is a very nice spectral plot. Axes are labeled. There's a grid to help you eyeball where your peaks are. So try and produce spectral plots that look that provide information like this one does. Okay. The other kind of visualization that's very useful is a time frequency plot. So we call these spectrograms. And first let me show you what they look like, and then I'll show you how MATLAB makes them. It's actually one line of MATLAB code will produce this plot. What a spectrogram does is it shows frequency on one axis and time on the other axis. So this was again a wave file that I recorded where I was whistling a tune, and I should have put a color bar on this plot so that we could see what the intensity values are. But red represents locations where there's energy, and then blue and green represent places where there's not energy. So basically just looking at this, you can see, and looking at the frequency axis and the time axis, you can see essentially what notes were being whistled and how long they were being held. So it's almost like looking at a musical score. I was actually whistling a tune here from the musical Sound of Music, and if you're musically inclined, maybe you can tell what I was whistling here. Anyway, this is called a spectrogram. It's a time-frequency plot. Again, this shows how energy is distributed across time and across frequency, whereas a spectral plot doesn't have any temporal information at all. It just says that for the data that was passed in to the FFT command, it just shows what the spectral content of that data is. So over that window, over that time window, this shows the spectral content, whereas a spectrogram will show you both time and frequency. I should note that this is an image. What's being displayed here is an image. It's a two-dimensional array where every row in that array is the output of an FFT. I mean, the way Matlab computes spectrograms is by calling FFT over and over and over again and building up a 2D matrix where every row is the output of an FFT. Let's look at how this is done in Matlab. So once again, I read in the whistling wave file. I choose an FFT size. In this case, it's 256. The actual spectrogram command is this. It takes in data. It takes in a window. It takes in an overlap size. So this is how far you want to shift your window each time you move it along the signal. It takes the FFT size, and then it also takes in the sample rate so that it can produce properly scaled frequency and time axes. And here I'm just showing an example. I choose FFT size of 256, an overlap of 80% of the FFT size, and I use a Hamming window for my window. We'll talk more in class later in the semester about different window shapes and what the effect is. But essentially, this, with just a very few lines of code, you can produce spectrograms and get these time-frequency representations of your signal. The rest of this is just setting the font size on the axis. It's turning on a grid and then making a PDF plot of the figure window so that I could include it in this report or this set of slides. Okay, so in summary now, we have talked about different kinds of signals, and we've seen how when those signals get loaded into MATLAB, they come in as multidimensional arrays and they're represented as multidimensional arrays. So we've also taken a look at manipulating multidimensional arrays, accessing and setting those arrays, slicing them, squeezing them, and permuting them. Those are the important things that we need to get out of all of this. I'm going to stop the recording here before I jump into the actual assignment, and I'll pick it back up right here where we leave off.